Ever wonder how scientists delve into the molecular world, unraveling the intricate details of chemical structures? The answer lies in a powerful analytical tool, nuclear magnetic resonance, or NMR, spectroscopy. Nuclear magnetic resonance spectroscopy is a technique that exploits the magnetic properties of certain atomic nuclei to provide detailed information about the structure, dynamics, reaction state, and chemical environment of molecules. It's a key player in the field of analytical chemistry, and its applications span far and wide, from the study of biomolecules to the analysis of complex mixtures. The heart of NMR spectroscopy lies in the phenomenon of nuclear magnetic resonance. This happens when atomic nuclei in a magnetic field absorb and re-emit electromagnetic radiation. This radiation often falls within the radio frequency range, and by measuring this, scientists can gain invaluable insights into the structure of the molecule. But how does this work exactly? Firstly, it's important to understand that not all atomic nuclei are suitable for NMR. Only those with a non-zero nuclear spin like hydrogen-1, carbon-13, or nitrogen-15 can undergo nuclear magnetic resonance. This spin gives the nucleus a magnetic moment, allowing it to interact with an external magnetic field. When placed in a strong magnetic field, these magnetic nuclei orient themselves with the direction of the field. They can either align with the field, a low-energy state, or against it, a high-energy state. Usually, more nuclei opt for the lower-energy state, but when the right amount of energy, that radio frequency radiation we mentioned earlier, is supplied, some nuclei flip from the low to the high-energy state. Once the energy is removed, the nuclei return to their original state, releasing energy in the process. This energy release is what NMR spectroscopy measures. The frequency of this energy corresponds to the difference in energy between the two states and is specific to each type of nucleus. This means that NMR can identify different types of nuclei in a molecule, offering a detailed picture of its structure. But NMR spectroscopy doesn't stop there. It also provides information about the chemical environment of the nuclei. This is due to a phenomenon called chemical shift. You see, the exact frequency at which a nucleus resonates depends not only on the type of nucleus, but also on its surrounding electrons. These electrons shield the nucleus from the external magnetic field, causing it to resonate at a slightly different frequency. By measuring this shift, scientists can infer details about the molecular structure. Finally, NMR spectroscopy can reveal information about the dynamics of molecules. Through a process known as spin-spin coupling, nuclei can interact with each other, causing splitting in their NMR signals. This splitting provides insights into the relative positions of atoms within a molecule, shedding light on its three-dimensional structure. To summarize, nuclear magnetic resonance spectroscopy is a powerful analytical tool that provides a wealth of information about the molecular world. It works by exploiting the magnetic properties of certain atomic nuclei, allowing them to absorb and re-emit electromagnetic radiation in a magnetic field. Not only can it identify different types of nuclei, but it can also reveal details about their chemical environment and their relative positions within a molecule. It's a key player in the field of analytical chemistry, and its applications are as diverse as the molecular world itself.